Thank you so much for the invitation. I'm so happy to see you all here. So what I'm going to talk about today is magnetic flux emergence and eruptive activity in the sun. So this is a brief overview of my talk. There are three main topics that I would like to talk about. One is the flux emergence. The other one is large-scale eruptions, and the other one is eruptions on smaller scales. So basically, I would like to connect these two things and how flux emergence basically drives some of these eruptions on different scales, and also how eruptions drive other interesting phenomena. So what you see here on the left-hand side is basically a full disk magnetogram of the sun. So in black and white areas, you see oppositely directed magnetic fields, positive and negative, and you see them that they appear in the photosphere in specific locations, and these are, as you know, the active regions. On the right-hand side here, you see a close-up of one of these areas where you clearly see the appearance of bipolar region. This is the positive, this is the negative polarity. So what we think that it happens is that magnetic fields that they rise from the solar interior below the photosphere, they may have a kind of a flux tube-like structure, and due to buoyancy and also the interplay between convection and magnetic fields, they rise, they are bended, they form a kind of a loop-like structure, and when they intersect with the photosphere, they create this bipolar region, and these two polarities, they're joined by magnetic field lines. And then, of course, when flux emergence continues, and these magnetic field lines will expand into the stratified atmosphere above the photosphere, and the magnetic pressure inside will make the field to expand. And then we see all these beautiful magnetic loops that they connect opposite polarities in active regions and so on. Now this is theory, obviously, and one can attempt to apply these theoretical ideas on numerical simulations and do something very basic, namely take a three-dimensional box, put a kind of a monolithic magnetic flux tube at the lower part of this numerical domain, which is, let's say, the under the photosphere region, which is convection zone. You can put some twist here, so you can see, for example, these blue lines are magnetic field lines which are twisted along this structure, the flux tube. Then include a stratified atmosphere in the background, and then put a density deficit, for example, inside your tube. Density deficit means that you can make one part of this tube more buoyant, less dense, and therefore more buoyant. And it will rise to create this kind of a magnetic loop that you saw before. Although this kind of initial setup sounds like very simple, in practice it's not so simple, because of course you have to have equilibrium at the beginning and include the stratified atmosphere, which by itself includes different layers. So what you see here on the right-hand side is the stratification of the plasma along height, somewhere here at the center of the tube. So this is the top boundary, this is the bottom boundary, this is the top boundary of the box. And if you look at this red line, which is the temperature stratification, so you see this is the convection zone, this is photosphere, this corresponds to the transition region, and this is corona. So here, these numbers basically don't tell you anything because this is dimensionless, but the temperature here is about 1 million Kelvin, so kind of an average temperature in the corona. So we have basically 5 different layers, including the chromosphere here. We put the magnetic field here, which is the cube. This is the magnetic pressure, which corresponds to this magnetic flux cube here. And then we try to push the magnetic flux cube so that it will emerge to the photosphere and above, okay? So these are the basic initial conditions in this kind of experiments. And because before I mentioned a density deficit, so you see here, for example, how density deficit goes along the tube. So you have a long density deficit in the middle of the tube. That means, because it's a deficit, that means that the density inside the tube is much less than the density outside. And obviously, it's less than at the center than at the edges. And because of that, the tube will develop a kind of a loop-like structure as it emerges, and it will continue to emerge in the photosphere and so on. And for those who like maths, these are basic equations that we're using for the magnetic field below the photosphere, also the density deficit, and so on. And you see typical values for the parameters that we have in the system, such as the radius, twist, and so on. But we can come back into that if someone has questions. So after we initiate the experiment, so what we see, let's go directly to the evolution of the tube. So what you see here is magnetic field, stronger magnetic field closer to the center of the tube. And as you go out, you have less magnetic field. This line here shows corona, 0 is photosphere. And what you're going to see is the development of this loop-like structure, the emergence of the field, and the expansion of the photosphere. So let's have a look. So the expansion, then it stops a little bit on the photosphere. There is a good reason for that. Then it expands into the outer atmosphere in the corona. This is not the end of the experiment, but this is enough to understand how emergence works, at least in a qualitative manner. So if you look at it from the other side, what you're going to see again is the tube which emerges, reaches the photosphere, then it starts to expand. An interesting thing here is the strongest field remains at or below the photosphere. The weaker part expands into the corona, okay? So if you look now this emergence phase from above, that means that if you are at the top of the box and you look downwards and you look at the photosphere, this is the magnetic field, the bipolar appearance at the photosphere, okay? So what you see here is positive and negative polarities of the magnetic field. Is the intersection of the loop-like structure of the magnetic field of the photosphere. Now, there are a couple of things here which are interesting. Just to save a little bit more time, I will focus only in one of them. So you have the 2 polarities that they pull apart, let's say, but between them, there is a strong polarity inversion line. And the one thing that I would like to mention here, which is very important to understand also the eruptions in the second part of my talk, is the shearing. There's a lot of shearing and very strong shearing, okay? This is magnetically driven. It's driven by the Lorentz force, okay? I don't want to go into details here, but the shearing happens on the 2 sides of the polarity inversion line. And because of this shearing, the field lines come closer together and they form new structures, okay? This is something also that you see in the observations, right? The shearing and the strong polarity inversion lines. We'll come back into that because it's a major factor for understanding the eruptions. But here, also, another thing which connects this slide with the next one is the magnetic tails. What you see here, below behind the 2 main polarities, is these structures here, which we call them magnetic tails. And just to show you that simulations are not very far away from observations, even if we start with something which is very basic, namely basic initial conditions, basic monolithic structure, flux tube, and so on. This is observations of an active region, positive negative polarity. They move apart, strong polarity inversion line, magnetic tails. And this is from the simulation that I showed you before, okay? And magnetic tails is, for example, an indication that you have a twist below the photosphere where we can't really have very detailed observations, except from HelAS seismology. But I don't want to go into that. I'm just saying here that, you know, using even the simple profile for the magnetic field and so on, you can still get flux emergence structures and the manifestation of flux emergence, which is comparable with what you get from observations. And it's not so simple always, namely what you get if you include the magnetic field lines, try to understand the magnetic skeleton, the connection between the different structures, include also current seeds in this emerging active region, then you see that nothing is simple here. It's very complex. So this is from the simulations, this is obviously observations, and there is a lot of heating in these current seeds. As you see, you don't have simple and small and monolithic filaments of current seeds here. You have a network of current seeds where you have acceleration of particles, you have a lot of heating. Again, I don't want to go into that. There are other people, Lucas Vlachos, Hans Isliker, Tasso Anastasiadis, Manolis Georgoulis, they have done a lot of work on these things, and I don't want to go into that in details. But anyway, what I want to show you here is that there is a lot of there are a lot of different things which are happening during the emergence. And again, I want to highlight the fact that although you start with something simple, you end up with something very, very complex here. So this is the formation of sigmoidal active regions, basically. So you start with a twisted tube, then you get active regions that they have this sigmoidal structure. And you know from observations that sigmoidal active regions, they're actually very good nests of eruptions. This is from the same simulation. You see how complex the current distribution is at or just above the polarity inversion line. Okay. So the second part of my talk is about eruptions, and I will go through very basic observations, then one slide on theory, and then simulations on large-scale eruptions, and then smaller scale eruptions, okay, which are jets, large-scale eruptions, CMEs. Most of you have seen that, kind of an old, basic, but classic observations on coronal mass ejections. So what you see here is kind of a huge explosion. Tons of plasma are ejected into the interplanetary space towards Earth. We know that this is this kind of eruptions, large-scale eruptions. We're talking about hundreds and hundreds of megameters in terms of size. It's a key factor on understanding space weather and Sun-Earth connection. We're talking about very high speeds here. And if at some point now here, if I stop this, then we see the kind of the core or the eye of this large-scale eruption. And we think that we may have a kind of flux robe or bended flux robe structure somewhere there in the middle of this huge explosion, the coronal mass ejection, okay? Now, if we go in smaller scales, and I'll play this movie now, which is observations 304 Armstrong and 193. So what you're going to see is this black structure here is a mini filament, and this will erupt. Okay, this is cool material, and then you'll have an ejection, cool and hot material, but it's not like the coronal mass ejection. However, this is what you're going to see is a kind of a jet-like structure and is driven by eruption. So you have eruptions here, you have eruptions there, right? So here we're talking about a jet, here we're talking about a coronal mass ejection. So let's have a look here. So if you look at this kind of mini filament structure, it erupts and then it drives, the eruption drives the ejection. Okay, then you have also reconnection and all these beautiful processes which are happening, but you have this kind of very nice vertical upward ejection of cool and hot material. Okay, so since I talked about flux robes, just a kind of a reminder of some very basic theoretical ideas of how we can have formation of flux robes somewhere in the solar atmosphere or below, let's say in the photosphere and so on. So this goes back to 1989, Van Balagoen and Piet Matlins So they saw this kind of scenario where you have magnetic field lines, polarity inversion line, shearing that you mentioned before, then magnetic field lines come together. They are oppositely directed. If you look at the arrows here, they show the direction of the field lines. When they come together, they reconnect. Okay, reconnection is a universal process, very, very important. They reconnect, they form longer field lines and shorter field lines. These shorter field lines, these loops, they can go down or they can go up. They can submerge or they can emerge, okay? But we're not interested about this. What we're interested about is that there are more field lines outside of this long field line, and if you apply the same process, you can have again reconnection. At the end, you form this kind of flux rope, okay? So now we're trying to see whether we can apply this in numerical simulations, either by hand. There are a lot of people who are doing this, or maybe it happens self-consistently. So you have a magnetic flux tube which emerges at the photosphere, you have the active region, you have polarity inversion line, shearing. Maybe this scenario happens self-consistently. So you don't have to do that by hand. And this is indeed what is happening. So in the simulations, for example, now I'll show you some snapshots of the simulation that I showed you before, but we go a little bit further on time. So this black and white area is the bipolar emergence that you saw before in the photosphere. And here is this kind of set of field lines, different kind of field lines that are traced from different points here and so on. Again, just to save time and be on time, I just want to show you how these magnetic field lines evolve over time, and I don't want to go into details, but what you're going to see is that you see that you start stretching the field lines, and some of these field lines now become longer, and you start forming a kind of flux rope. And if you look at these field lines over time, I mean, basically they follow the scenario that I showed you before, okay, by and Belagoin and Pitt Martins. And at the end, you form a very nice kind of flux rope, and this flux rope erupts. Underneath the flux rope here, there is a current seed, and as you see, these green field lines now, which is not part of the flux rope, they will actually reconnect, and they will be part of the flux rope. So as the flux rope, actually, this new flux rope, not the original one that we have below the photosphere, okay? This is a new flux rope, which is formed just above the photosphere because of shearing and reconnection, okay? So these field lines, they will reconnect here. This is what we call tether cutting reconnection, and they will become part of the flux rope, which as it erupts, it grows in size, okay? And so we will talk a little bit about this. Now, one thing very quickly is that if you look at this flux rope during its formation, during its evolution, you can follow the core, let's say, of the flux rope. You can trace the speed, you can trace the height of this flux rope. If you make a height time profile of the core of the flux rope, you see that initially it grows, let's say, linearly. At some point, you have a kind of ejection. This is typical profile for an eruption, as you know also from observations, okay? You have this flux rope which erupts with high speeds, and obviously something happens here, right? And this is the onset of this kind of eruption. Why this is happening is another matter, right? Now, let's have a look on how this goes in numerical simulations. So you see, oops, let's play it again. So you see the cross-section of the magnetic flux tube, it emerges, and then we have first eruption, second, third eruption, and another one. So what you see in terms of eruptions is just this magnetic flux which erupts. But the interesting thing is that you have a recurrent ejection of plasma, okay? Now, if you look on 3D field lines together with the vertical velocity, so what you will see here based on this color panel is the vertical velocity. So red is positive, blue is negative, so you will see red and blue, that means a good sign of reconnection. Okay, and you will see the red and blue just below, underneath the erupting flux rope. This is the original flux tube, and you will see the field lines now and how they form this magnetic flux rope and how this magnetic flux rope erupts. So it emerges, and then that is the first eruption, second one. It's a bit messy, third one, fourth one, and so on. So you see red and blue, this is because of reconnection, okay? So let's speed up a little bit. I'm talking about eruptions. Obviously, you can compare with observations in a qualitative, but also in a quantitative manner. I mean, I gave you some numbers about velocity, density, temperature, and so on. Here, what you can do is to produce synthetic images of these eruptions. This is just one snapshot of one of these eruptions. And if you, I mean, I'm sure that you can find observations of this. So more or less the same kind of structure here, like the core of the erupting field, kind of a cavity, okay, the edge, and also flare. The flare which happens underneath the erupting material, and this is in these current seeds that I show you, that they have this kind of sigmoidal shape, and the heating there is very intense. We're talking about 5, 6 million or 10 million, okay? And you have hot and cool material now also which erupts. An interesting question is whether indeed what you see in the box could be a CME or a small CME. And there are two ways to figure it out. One is whether you have a huge box, numerical domain, talking about numerical simulations, let's say hundreds and hundreds of megameters. And, but this, in most of the cases, is not feasible yet. Or you can take what you have and based on the numbers that you get, you can make an extrapolation and see whether indeed your erupting material in your simulations would actually develop or evolve into a CME or a CME-like structure. So here, this is the numerical domain that we have in a typical simulation, all right? This is the interpolation. So what you saw before, this kind of a flux rope which erupts, or one of them, I mean, the eruptions were recurrent as we saw, at 0.6 solar radius, for example, it will have a length of around 100 megameters or more, and the energy will be 10 to the 28 ergs. And the velocities, obviously, they are very high. We're talking about 100, 300 kilometers per second. And according to observations, this might account for small CMEs. Now we're running
5 more minutes, Vasily.
Sorry, Tasso?
5 more minutes.
Okay, thank you. So now let's go to small scale eruption. So you saw the movie before about this cool material which erupts. So you see again the same thing, the small material erupts, but now it gives the onset of the ejection, but in a different manner. So obviously this is more like a jet, okay? So what happens here? In theory, what happens, and this is from Moore in 2010, is that you may have flux emergence, you may have still strong polarity inversion line and formation of a flux rope, as we described it before, and this flux rope can erupt, okay? And the reconnection between the erupting flux rope and the pre-existing field can actually lead to this ejection of cool and hot material. Cool because it comes from the filament which erupts from the lower atmosphere, and hot because you have reconnection with the pre-existing field. If this is what is happening, this is a very different mechanism for the onset of jets, because the typical scenario for the onset of jets for 40, 50, 60 years now was just reconnection between, let's say, an emerging field and pre-existing field. Here we're talking about a completely different driver, and the driver is the eruption. So this is simulations that we tried to see whether we can actually produce this kind of jets driven by eruptions. Flux tube, ambient field. So indeed we will have reconnection between these two when the magnetic field will emerge. So you see here a cross-section of this kind of experiment, and when the emerging magnetic field with the ambient magnetic field come into contact, they create the current seed, oppositely directed magnetic fields. A kind of nice spire here. You see the jet, and you see also the bright point on the right-hand side, which might account for a flare. However, you saw before that you have eruptions here, right? So this is the emerging field, but after this emergence process continues, you will have a flux rope here which will emerge, which will erupt. And what happens then? Well, this is a movie which shows this experiment, density and temperature. So what you will see is the eruption of the flux rope after the emergence. Here is the eruption now, and the creation of a very nice jet, which is much, much wider than the tiny Eiffel Tower jets and so on. And you have cool and hot material here. And also you have these bright structures on the left side, on the right hand side and so on, which are actually key features of the observations of this kind of jets. So again, you can create pseudo-synthetic images. This is 193 Armstrong, where you can compare the simulations. This is from simulations with observations. So this is one slide before the last one. And I just want to show you some of these simulations. This is 2013. And again, this is 2013, just I think it's 1 month difference actually in the publication date between these two. And that is 2017 Nature from Wire Spiro until Hohenn-de-Vore. And all these simulations actually show exactly this process, namely jets are driven by eruptions. So again, this is something new. It's a very hot topic these days because it changes our view on how jets basically are triggered. And so it is very interesting to understand eruptions on different scales. I guess that is the message. And larger scales, you can have large-scale eruptions, CMEs, and smaller scales, you can have jets, for example. So I would leave you with this slide here, very, very briefly to say that I think that now, after so many years, we understand flux emergence, some very basic features in flux emergence as we observe them also in the sun. The second thing is that we can create flux ropes, which are also basic features on eruptions. Okay, we think that we have formation of flux ropes, which are actually drive eruptions. On small scales, they create jets. On larger scales, they can create, like CMEs. So here, what we're talking about is a kind of a unified model for jets and CMEs based on eruptions. And the mechanism of eruptions is mainly related to reconnection, either breakout or internal reconnection, which is tether cutting, and or instabilities like torsion stability. I haven't talked about this, but it's in our papers. Now, the work in progress is, first of all, try to understand convection. I didn't talk so much about convection and the interplay between convection and magnetic fields on the formation of pores. This is work in progress. We have done this, soon we will publish something on the formation of pores. This is very, very interesting. The other thing is dynamo. These magnetic fields that we have used, they're not dynamo generated, okay? We put them by hand, but we know that magnetic fields are generated by dynamo, so we have to use dynamo. And the last thing is, can we go even on smaller scales and see whether this kind of model still works? Namely, if eruptions can drive the onset of other phenomena too. So I would like to leave you with that, and thank you so much for attending this.
Okay, thank you, Vasilis. Do you have any questions? So let me. I haven't seen any question on the chat. Now let me, if someone wants to unmute himself, then he can do it now, and then he can ask a direct question. We have a very short time of asking questions.
Hello, Vasilis.
Hello. Hi, Spiro.
Hey, how are you doing? Excellent talk. Very nice talk. Very clear.
Thank you.
I have a question and a comment on your emergence simulations.
Yeah.
Normally, when you think about the flux cancellation picture, like from Balahoyen and Martins, what you think about it is that occurs at the photosphere, and that leads to the formation of a stable filament channel, which sits there before it eventually erupts. But in your simulations, it looks to me as if what you're seeing reconnection down below there. But doesn't it look to you as if it's really the flare reconnection, in the sense that it's due to a current sheet that forms above the photosphere and is part of the eruption process? So it's
Yes.
very hard to distinguish between the this picture, which happens at the photosphere, and the flare reconnection, because they both lead to the formation of the twisted flux rope. Really, it's a question of, does it happen well before, or does it happen as part of the eruption process and in the corona? So what are your comments on that?
Yeah, I mean, that's a huge topic, Spiro, and I guess is a key open question.
Just give a short answer, please, because we are running out of time.
Yeah,
anyway.
yeah, it's a key open question. This is what I want to say. I mean, I think that it's not only one or the other. It's not only flux cancellation and it's not only the flare reconnection. I think we have both. In our simulations, we haven't studied the flux cancellation, but I can't say that flux cancellation is not as important as the flare reconnection. I think my view on this is that both are important, but I can't comment on flux cancellation because we haven't studied the flux cancellation. But I know that it's important, and I have seen hints from observation that it's important too.
Okay, we need better and more emergence simulations, and you're the man to do it. Thank you.
Including convection, Spiro, because flux cancellation.
Yeah. You're completely right.